All right, so now here's another interesting aside. Okay, before we go into the slide, let me mention. So again, here's the Earth. The space shuttle orbited about 250, 300 miles above the surface. I mean, the space shuttle orbits about 300 miles above the surface of the Earth. So it's the radius of the Earth is 4,000 miles. So it's about 10% the radius of the Earth. Okay, so it's not very far away, and the orbital period of the space shuttle is about 90 minutes, roughly. So just keep that in mind. Okay, so let's go back to this example that we're talking about. Okay. Now, so here's a thought experiment. So let's say we dig a hole through the center of the Earth. Now, if you drop an object in this hole, it turns out that the motion of this object would be just like a mass, just like that of a mass attached to a spring. Okay. And this mass would oscillate back and forth, go back and forth. And just like that, this object would oscillate back and forth. We'll see this in one of the next chapters. The force on the mass, the force that the spring exerts on the mass is given by this formula, F equal to minus kx is given by F equal to minus kx. X is that distance, okay? The distance from the equilibrium position. K is called the spring constant, and so on. The force on this mass in this hole is given by this equation, and this is exactly like the spring constant, and R is the distance from the center of the Earth, which is exactly like X. Okay, so the motion of this object will be just like the mass attached, exactly like a mass attached to a spring. All right, so now things get even more interesting. Oops. Where was the period? Okay. Oh, yeah. So and so for this, so you saw that the mass dropped here will oscillate back and forth, and you can calculate the period, and the period would be the time it would take for this object to go down there and then back up. Okay, and that would be 84 minutes. Okay, exactly the same time it takes for the space shuttle to go around the Earth. Okay, now, and those are related. So we'll see in chapter 15, we'll study simple harmonic motion. So this object falls down, and what happens is it's going the fastest at the center of the Earth, and then so if you drop an object in this hole, it'll start speeding up, and it'll be going the fastest at the center of the Earth, and then start slowing down, and it'll come to rest there, and then back and forth. Okay, keep repeating. The speed of the object at the center would be about 18,000 miles an hour. Okay, which is exactly the speed of the space shuttle going around the Earth. Okay, so anyway, the point is this simple harmonic motion is related to motion at constant speed around in a circular orbit. Okay, so that's the interesting part. Anyway, what this slide shows you is so the acceleration due to gravity at the surface of the Earth is 9.181 meters per second square. Okay, so that's what's shown here. at the surface of the Earth is 9.81 meters per second square. And if you are above the surface of the Earth, it falls off like so. Okay, so if you were 1 radius above the surface of the Earth, the acceleration due to gravity is about 2.5 meters per second square. Now, if the Earth's density were uniform, this would be the acceleration due to gravity inside the Earth. Okay, so if you were at this depth, that would be the acceleration due to gravity. At the center of the Earth, it's 0. Now, this is because the density of the Earth is not uniform. This is the more realistic. This is how the acceleration due to gravity varies with depth. So the strongest acceleration due to gravity is at about 3,500 kilometers from the center of the Earth. Okay, so that's what that graph is showing you. Okay, I will not go through some of the derivations because we have too many slides to go through. All right, so in one of the previous chapters, you saw that the gravitational potential energy was given by mgh, where h was the height above the surface of the Earth. So that was the gravitational potential energy. Now, this is an approximate expression, and this is good enough as long as you're close to the surface of the Earth and g does not vary. But you saw that if you find yourself traveling fairly far away from the surface of the Earth, g varies. Okay, and if g varies, then this expression this is not a good expression to use. Okay, so if you work for NASA and if you go on interplanetary orbit journeys and stuff like that, the potential energy between two objects, the gravitational potential energy between two objects is given by that expression. That's the more accurate expression. It's just that this is a pain in the neck to use, and so if you're close enough to the Earth and you don't go too far away, you use this expression. Yeah, but this is the more accurate expression. So the gravitational potential energy between two objects is given by this expression. So the gravitational potential energy between the Earth and some mass is gmm minus gmm divided by the distance between the two objects. So if you have an object here, the gravitational potential energy between these two objects would be mass of this object times mass of that object, g minus g times that divided by the distance between them. Okay, so that's the more accurate expression for acceleration, the gravitational potential energy. Okay, so, and with this expression, the gravitational potential energy goes to 0 at r equal to infinity. So now if you wanted to calculate the potential energy of a system of particles, so if you wanted to calculate the gravitational potential energy of the solar system, for instance, you'd calculate the potential energy of these two bodies plus these two bodies plus these two bodies. You'd calculate the gravitational potential energy of all independent pairs and then add them up. So that's how you'd calculate the potential energy of a system of particles. Now we'll talk about something called the escape velocity. What escape velocity means is the following. So let's say this is the Earth. Now you throw an object up. Okay, let's say you throw a baseball or something. It'll go to a certain height and come back. Now you throw it harder, it'll go higher and still come back. Now the question is, can you throw an object such that it never comes back? It goes away to infinity. And that is escape velocity. it turns out that from Earth, okay, so when you throw a baseball, you're probably throwing it at about, we'll just say 10 meters per second. Okay. That's 25 miles an hour. Now it turns out if you throw an object at 11 kilometers a second, that is 11,000 meters per second, then the object will never come back. Okay, and that is escape velocity from the surface of the Earth. Now it turns out that if you're throwing something at this speed, you can throw it in any direction and it'll never come back. Okay. So escape velocity is defined as minimum speed needed to allow an object to move infinitely far away from Earth. And the escape velocity is given by this expression, 2gme divided by r, the radius of the Earth. So this, of course, is a general expression from, so the escape velocity from any object is 2 times g, and that is the escape velocity from that distance from the object. So from the surface of the Earth, the escape velocity is 11 kilometers a second. You can calculate the escape velocity from the Earth from this distance, and that'll be lower. But anyway, you can calculate the escape velocity from any point. So the escape velocity is 11 kilometers a second. And the International Space Station travels at 8 kilometers a second. And so that's why it does not escape from the Earth's orbit. Okay, remember, you need 11 kilometers per second. So every orbiting satellite, you know that its speed is less than 11 kilometers per second. Every low Earth orbiting satellite, its orbital speed is less than 11 kilometers a second. Okay, so hopefully now you understand the concept of escape velocity. Okay, so here are escape velocities. Escape velocity from Mercury is 4.3 kilometers a second. From Earth, like I said, 11 kilometers a second. So if you found yourself on the surface of the sun and didn't burn yourself, the escape velocity from the sun would be 618 kilometers a second. Now here's an interesting idea. You guys all know that nothing can travel faster than the speed of light. Okay. So now you can take an object, and what you can do is start squeezing it. So decrease its radius. And when you decrease its radius, this gets bigger and bigger. And the escape velocity from that object gets bigger and bigger. So it gets harder and harder to escape from this object. So you took this object and you're squeezing it smaller and smaller, and the escape velocity is increasing. Okay. What if you squeeze it to such a radius such that the escape velocity becomes equal to the speed of light? You squeeze it smaller and the escape velocity becomes greater than the speed of light, and nothing can escape from it. And that is a black hole. Okay, so a black hole is an object. Okay, so all right, so we'll talk about it more. So anyway, so okay, so here is the sun, and the question is, what would it take to make the sun into a black hole? By the way, the radius of the sun is about 700,000 kilometers. Okay. And it turns out that if you squeeze the sun to a radius of the Schwarzschild radius is what it's called, to a radius of about 3 kilometers, then the sun will turn into a black hole. So when you have squeezed the sun to a radius of 3 kilometers, at this point the escape velocity is the speed of light. And as it turns out, if you squeeze it to that point, there's no stopping it. It'll all fall into the center, and we don't know what happens at the center yet. But anyway, so it'll collapse, and we don't know how far it'll collapse right now. Well, according to Einstein's theory, it will all collapse to a point, but we know that that's not true. So if you squeezed our sun to a radius of less than 3 kilometers, then the escape velocity would be greater than the speed of light, and the sun will have become a black hole. All right, so here's an interesting fact. Knowing the escape velocity from a planet and the average temperature on the surface of the planet, you can calculate what kind of atmosphere the planet will have. So for instance, the moon, because of its low escape velocity, the moon has no atmosphere. Any gas you put on the moon's surface will escape, okay, and so on. So that's, so here's the key fact. If the average velocity of a gas molecule, which depends on the temperature at the surface of the object, is 1/6 the escape speed, then the gas will not be present on the planet. Okay, so anyway, so that's why the moon is, any gas you put on the moon, it'll escape. All right, here are pictures of a, so here's a cone, and you can take various conic sections. So there's the base of the cone. If you take a section parallel to the cone, what you get is a circle. If you take a section that is at an angle to the base, you get an ellipse. Okay, and if you take a section perpendicular to the base, you get a hyperbola, and at an angle which is intersecting the base, this is a parabola. Okay, so why are we talking about these things? Okay, so what we are interested in is the following. So here's a body, and if so, this could be the sun. We are interested in various orbits around the central body. So if so, here's the central body. This is what is called a bound orbit. Okay, a bound orbit is well, it's this object is not escaping the gravity of this object, of the central object. Okay, so this is a bound orbit, and it turns out that bound orbits are either circular or elliptical. And for bound orbits, the total energy, which is kinetic energy plus potential energy of the object, is less than 0. So for these two orbits, the total energy is less than 0. For a parabolic orbit, if this went on a parabolic orbit, the total energy is exactly 0. If the object goes on a hyperbolic orbit, this is a hyperbolic orbit, the energy is greater than 0. Okay. So bound orbits have energy less than 0, and the orbits are either elliptical or circular. Unbounded orbits, for parabolic orbits, energy is 0. For these orbits, energy is 0, and hyperbolic orbits have energy greater than 0. Okay. So of course, all planets have elliptical orbits. They're all bound to the sun. Okay, and so on. And most planets don't have circular orbit because there are a lot more ellipses, and it's more than likely, I mean, the probability is higher to have an elliptical orbit. All right, and so that's the conic sections, and there's some of the details here of the conic sections. So all planets have elliptical orbits. The sun is at one of the focal points, the other focal point is empty. Okay, and so on. And here is the equation of a conic section in polar coordinates. Okay, you guys can review these slides. I'm not going to go over them too much. So here's the equation of an ellipse. in Cartesian coordinates, and so on. In this formula, E is the eccentricity of the conic section. E is the eccentricity, and alpha and E are determined by the total energy and angular momentum of the satellite. Okay, so alpha is another constant. All right, so planetary orbits are ellipses. So here's a hyperbola, and here's the equation of a hyperbola, and so on. Again, I'll let you guys review these. Here's a parabolic orbit. Here's a parabolic orbit. Again, in a parabolic orbit, the energy of this orbiting particle is zero. Total energy is zero. Okay, so Kepler's law we'll talk about. So Mr. Kepler discovered his laws about 300 years ago. Okay, so what Mr. Kepler found was what Mr. Kepler discovered from some of the observational data that Tycho Brahe, his boss, had taken. What he surmised was all planets go in elliptical orbits with the sun at one of the focal points. All planets move in elliptical orbits. The second law states that the radius vector, so there's the radius vector drawn to the planet, sweeps out equal areas in equal time intervals. So this radius, the radius vector has swept out this area. Okay, so what Mr. Kepler is saying is the following. If a planet covered this distance in 1 month, so it swept out this area. In another month, some later month, the area swept out, this area will be equal to this area. Okay, so areas swept out in equal time intervals are equal. And that's what Mr. Kepler found. And the third law says the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Okay, so it's better stated for a circular orbit. Most planetary orbits are almost circular. What Kepler is saying is for all planets, t square, the period, orbital period, divided by r cube, the radius cube for the planet. This is constant for all the planets. And it turns out it's related to the mass of the sun. Okay, the mass of the central, the object you're orbiting. Okay, so these are the three Kepler's laws. And so Kepler's first law that you're either in a circular or elliptical orbit is a consequence of inverse square force law. And that is, remember, the force of gravity is gmm by r squared. Okay, so the inverse square law. So bound states, energy less than zero, are elliptical or circular. Unbounded objects pass by never to return and have parabolic or hyperbolic orbits. So it turns out, by the way, that Mercury's orbit precesses. Okay. So this was an indication of the fact that the force was not exactly an inverse square law. Okay. And that, so, and Mr. Einstein, with his general theory of relativity, was able to, his theory was able to predict this precession of Mercury. Newton's laws were not able to do that. The perturbation of other planets could not account for this thing, could not account for the precession of Mercury's orbit. Okay, Actually, I'm going to pause now, and I will